Okay, how about this first one about non-competitive inhibitors?
Go onto the enzyme, but in a different spot as a substrate.
And really deform it so that stuff can't.
Substrate.
Yeah.
Okay, so what about that? Inhibitor attaches to the enzyme but not at the activity site. The inhibitor deforms the activity site, making the substrate unable to connect. So now the reaction can't happen. How about this chelation word?
Metals.
Is it with metals? It could be with metals. Anybody else? What about it with metals? It could be with anything, but
it'll allow it moves it to like either more or less vulnerable sites, right?
the chelator grabs whatever it is that it's intended to grab, like a molecule or an ion, probably a metal ion, and now it's no longer able to be that non-competitive inhibitor. So if somebody has arsenic poisoning, you can give an arsenic chelator, and the arsenic chelator goes and grabs the arsenic, pulls it off that enzyme, and then the activity site goes back to normal, and then the enzyme functions as it's supposed to. And then the body either disposes that through the kidneys or you poop it out, one of the two. But actually, it's just going to be a kidney thing. Yeah. I guess it could be something that's in the intestines, but probably not. So the problem with non-competitive inhibitors is, we didn't actually talk about this, is the substrate concentration. It doesn't matter because it can't make a connection anyway, so I don't care how much of it you've got around. So what you need to do is use something that will remove the non-competitive inhibitor, and that's what a chelator is. So if somebody's poisoned with something like arsenic or cyanide or lead or something like that, you would give them a chelator, and then that would remove that substance from activity. So stop it from interacting with an enzyme and causing problems. You would probably call it the antidote, but its technical name is a chelator, and the process is chelation. Write the balanced chemical equation for chlorine gas and ethane. All right, so C2H6 plus Cl2, and we're making chloroethane, so C2H5Cl plus HCl. Gas, 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 gas. And then write the equilibrium expression. So K is equal to C2H5Cl HCl C2H6 Cl2 close parentheses. Okay. So just the reactants in the denominator and the products in the numerator, and then this is just the ratio of the reaction. I should draw a backwards arrow on that reaction. It's a double-sided arrow, meaning we're in equilibrium. All right, acetic acid has a weak Ka. Write the equilibrium expression. Acetic acid dissociation. Okay, so we've got CH3CH2COOH. CH2COO negative plus H plus. And so then it's Ka is equal to H plus CH3CH2COO negative. And then CH3CH2COOH. Actually, I meant to ask more with that question, but whatever. All right.
Was what you were going to ask.
Well, it was going to be a question that we did in class the other day, where if I would have asked something like the acetic acid concentration is 0.25 molar. What's the H plus ion concentration? So how would we accomplish that? So I know from the problem that the Ka value is 1.25 times 10 to the negative fifth. And I know if I just said that this is going to be 0.25 molar acetic acid, all right, 0.25 molar, then I know that 0.25 goes down here. But remember, this is a double variable problem. There's an H plus up top and acetate up top, and I don't know what either one of those concentrations are, but what do I know about them? They have to be the same, so then I can just put an X for H and an X for acetate, and then I can resolve for X, or I can solve now for X. So if I solve for X, I've got 1.25 times 10 to the negative fifth times 0.25 equals X squared. That's a bad 2. Equals X squared. And so then X would be equal to the square root of 1.25 times 10 to the negative fifth times 0.25. And what would that be? Square root 1.25 e negative 5 times 0.25 close parentheses equals 0.0018 molar. All right. So this changes by a factor of 1, so nothing. This changes by a factor of 2, and this changes by a factor of 2. So it's going to be second order with respect to the oxygen. And this goes up by a factor of 2. That's a factor of 1. And this goes up by a factor of 4. I'm sorry. I did not mean to write that for the oxygen. It's second order with respect to the nitrogen dioxide, and it's first order with respect to the oxygen because they changed by the same value, but these did not. So then it's K is equal to rate divided by NO squared and O to the first. So I got 0.12 divided by 0.12 squared times 0.05. 0.12 divided by 0.12 squared divided by 0.05. And 167 for my K value. So then my rate law will be rate is equal to 167 NO squared O2 to the first. Are we good with that? Where? This two? Oh, the energy, yeah, that's product.